So this week we're going to talk about Chapter 6, Transform and Conquer. But first, just a quick update on the schedule. So this is the last week of material for the midterm. Okay, so we've covered chapters 1 through 6. 1 was mostly an introduction. 2 was on the whole idea of algorithmic efficiency. So we've been talking about that a lot. That's the big O, the big theta, the big omega, and the summations, things we were doing. And then we went into some techniques for problem solving. And the last of these is going to be in Chapter 6 on the transform and conquer. So the exam will be problems based on primarily chapters 2 through 5. Okay. So next week's video that should come out by Sunday will be a review video going over different things, what's important, what's not. You'll also have the problem sets to look at. I'll try to get some more of those graded as we go along. And then the exam itself, we'll probably do like last time. I'll probably make it available, let's say Friday through Sunday of next week. That would be my guess. If there are issues with that, then we can always adjust that as need be. Okay. Okay, so this chapter is on transform and conquer. It's the idea that, so before we're going to, decrease and conquer or divide and conquer, or change in some way and conquer. Okay, now we're talking about specifically, we're going to transform the problem into a different problem. Okay, so which can be tricky, but it can also be pretty effective. Okay, so the transform and conquer come into 2 stages. The first is that you have to transform an instance of a problem into another problem that's easier to solve. Okay, and then the second stage, you actually solve it. Okay, so there are 3 major variations on this idea. Okay, the first is that we're going to transform it to a simpler or some more convenient instance of the same kind of a problem. We're going to call that instant simplification. Okay, we'll talk about that in the first section. Okay, next we're going to get to this idea of you're going to transformation to a different representation of the same instance. We're going to call that representation change. Okay, and then finally we can change it to an instance of a different problem altogether, for which we can find an algorithm. Okay, for that to be true though, we have to be able to prove that we're transforming it correctly to the new problem. Okay, so in this chapter we're not going to cover everything in detail. There will not be homework from all the sections. I think some of them go beyond what is important for us. So we'll kind of talk about that as we go along. Okay, and that just went crazy because it does sometimes. Okay, so the first idea here in section 6.1, and this again, this is from this first section here, the instant simplification. We can often simplify a problem simply by pre-sorting it. Okay, so when you're looking at this, the first thing you have to figure out is you have to take the time to sort it first. Okay, so that's going to add at best an n log n. Okay, with a quick sort or a merge sort. Okay, merge sort is always n log n, but the quick sort, remember, is n log n in the average case, but it could also be quadratic if it's a really poor case, if the pivot points are chosen poorly. Okay, so n log n is the best algorithm is going to get. We're going to talk later about why that is theoretically true. Okay, we did chapter 11, but so we know that if we don't save enough time with the pre-sorted versus sorted, then we have to consider whether it's worth doing or not. Okay. So this first example, we're looking for element uniqueness in an array. Okay. So the idea is, do you have any elements that are there more than one time? Okay. So we did this back in section 2.3, and the brute force algorithm just compared pairs of the array's elements with all the other elements until 2 equal elements were found or there were no pairs to check. Okay. And the worst case efficiency of this was n squared. And again, the worst case efficiency, as I recall, is that there are no matching pairs at all. So you have to keep going until you found it. Okay. So if we sort the array first, okay, then you only have to worry about checking consecutive elements, because if 2 elements are the same in a sorted array, they're going to appear next to each other. Okay. So that really gets to be a lot more straightforward. Okay. So in this case, we can drop down this idea here from n squared down to n. Okay, which is pretty good. Okay, so if we add this n log n sorting algorithm to this, okay, then we're going to be able to still have a better than brute force. Okay, so remember this formula we covered back probably in chapter 1, maybe 2. So this idea then for the total that we're going to first sort and then scan, okay, it's going to be an element of this n log n and an element of n. Okay, so now n log n is bigger than n. Okay, so it takes longer to sort than it does to scan. But remember, by some formula, not a formula, it's called something else, a theorem or a lemma, that when we have two tasks, we only look at the time of the first task as being important here. Okay, so when you have an n log n plus an n, it just ends up being n log n because n log n is bigger. Okay, so it takes longer to sort than it does to find the unique pairs, which makes sense. But all of that combined is better than the n squared. Okay, because remember, log n is less than n, it's about half. So n log n is bigger than log n, but n log n is smaller than n squared. Okay, so that's just an example of how we would go through that. And in this case, again, we're just looking, the algorithm's pretty straightforward. We're just looking for the next element to see if it's the same. Okay, that's all we've got there. There's another one here of computing the mode, which you can go through, okay, and goes through that way, okay. And there's the pre-sort mode and all that stuff. Yeah, I think it's pretty straightforward. Okay, so there will be a couple of homework problems, 1 or 2 from this, okay. So the next section is on Gaussian elimination, okay. This is a really important concept that I assume you've probably seen somewhere along the way. There are other parts of this chapter, the LU decomposition and all that, which we're not going to worry about. But I do want you to be able to do Gaussian elimination. There will be a Gaussian elimination problem on the midterm. Okay. So Gaussian elimination, of course, invented by Carl Gauss, who created a whole bunch of cool stuff. But anyway, it deals with systems of linear equations. Okay. So we're going to do an example here with 2 linear equations and 2 unknowns, but you certainly can do n equations with n unknowns. Okay. And when we solve these by hand, it's basically you have to reduce it down to one variable, okay, by solving for an x or a y, whatever you have, and then put that in terms of, then plug that back into the first equation and then solve for the variable that way. Okay, that's how you're able to reduce it down to one variable and solve it there. So you would solve, so for one equation, you would take and solve it for x in terms of y or y in terms of x, whichever one's easier. Plug that back into your other equation and then solve for whichever variable you're left with. Then once you have one, you can plug it back in to get the other. Okay. So if you have multiple layers of these, and the book here is using A11, A12 to A1n for xn, then all the way down to AN1 x1, all the way to AN xn, okay, to show the system if there are multiple here, more than just the 2. We have multiple unknowns, okay? So you would solve this the same way you did before. If you had 10 unknowns, right, you'd have to solve first by getting rid of one of the unknowns and then one more and then all the way down. That would be complicated. So we have this idea here called Gaussian elimination, okay? So we're going to do this. So the idea here, so we're going to transform, again, I'm reading from here, a system of n linear equations in n unknowns, okay, to an equivalent system that's going to give us this upper triangular coefficient matrix that has a matrix with all zeros below its main diagonal, okay? And by doing that, in essence, we're going to solve it for one case in a much simpler way to do it, okay? Interesting here that I like the side note here that this is named after Carl Gauss, who's huge again in mathematics, but the method was known to the Chinese 1800 years before the Europeans rediscovered it. So whoever the Chinese mathematician was who did it, they get no credit because, yeah, that's how the world is. But anyway, So I thought that was an interesting historical side note. So what we're going to do here, we're going to solve this problem. So here's our problem. You know, it's still, we're going to get to a real problem in a minute, but we're going to have these A11, A12. We're looking at these are matrix notations all the way down to AN1 and ANN, XN, okay? And we're going to write this in matrix notation, okay, as AX equal B. X is our variable that we're dealing with here. And again, instead of doing different variables, X, Y, Z, which we would normally do, we're just doing X1, X2, Xn. It doesn't matter. You can substitute those around. This is just for simplicity, okay? So in this AX equal B, we're going to transform those the coefficients into a matrix, okay, and then finally have our B, which is what they're equal to, on the other side, okay, and then we're also going to transform that into an equivalent matrix that has zeros on the main diagonal and below, okay, and then from that we're going to get our answers, okay, and that's where little tick marks and little primes come in, okay. So that's going to tell us the difference there. So to do this, okay, we're first going to have to put our problem in terms of the coefficient matrix and the answer matrix. We're going to combine those together, okay, and then we're going to move to this arbitrary coefficient matrix A through the following steps, okay. We can exchange two equations if you want. You can move them around if you want. You can, here's the key part here, you can replace an equation with its non-zero multiple. Okay, so you can just multiply everything in a row by something, or you can replace an equation with a sum or difference of this equation and some multiple of another equation. That's how we're going to get to the zeros here. Okay, so when we look at an example here, I think this will make the most sense. And I think I probably have a video working through another example that I will try to find out. But if we have the following system, okay, so we have X1, X2, and X3. Those are our variables. Again, that could be X, Y, Z, but we're going to put them all in terms of X with subscripts to make it a little more efficient in our how we're going to write it, okay. So we have the following: 2x1 minus x2 plus x3 is equal to 1. And we have 4x1 plus x2 minus x3 is equal to 5. And we have x1 plus x2 plus x3 equals 0, okay. And from this, we have to determine what x1, x2, and x3 are such they meet all three equations. Okay, we call this linear equations again because we're talking about something that will form a line. Okay, so yeah, there are no powers here. I mean that's the point. Everything's single variables. Okay, so we're going to transform this into the matrix we're going to work with here by putting in the coefficients. Okay, so the first equation has a 2 for the x1, the second one has a 4 for the x1, and the third has a 1 here for the x1. Okay, the minus x squared, or x2, not x squared, sorry, is a -1, and then there's an x2 in the other two, which are just 1s. x3 is a 1, a minus x3 is a -1, and then x3 is a 1 there. Okay, pretty straightforward. Okay, we're going to add in this case, since n's equal to 3 here, we're adding an n plus 1 or 4th row for these values, the 1, the 5, and the 0. Okay, so if they were not in this order to begin with, I mean, you could move them around. Okay, we're not going to do that. Okay, but we could. So the idea here, when you see this 4, that's what you want to target. Okay, and you want to take some multiple of another row and add it or subtract it to this row, okay, in order to make that a 0. Okay, that's a transformation that you want. And whatever you do here, you have to do here everywhere else as well. We're going to do the same thing for this one. Okay, so we start with this one, the 4. Okay, so if we take this row 2, which we're on, and we subtract, okay, it's 2 times row 1, but we don't have to. In other cases, it may be more complicated. So we're going to say the 4 we have divided by the 2. Okay, in that case, that's because the 4 is a coefficient there and the 2 is the one on row 1. That way they're going to equal out and give us our 0. Okay, so that's the idea. So if we take row 2 minus 4 halves, row 1, okay, we're going to get here the 4 minus 4 over 2 times 2 is 4. So 4 minus 4 is 0. Okay. This is going to be 1 minus, okay, negative 1 times 2, basically. So it's negative 2. Okay. So negative 1 minus 2 gives us a 3. Okay. Sorry, the minus is going to go the other way. There's a minus with a negative that makes it a plus. There we go. To give us a 3. Okay. We do it with the negative 1 times 4 halves of 1. We get the negative 3. And then we get the 5 times 4 halves of 1 gets us a 3. Okay. So we've now transformed this row via this mechanism. Okay. We do the same thing here. We've got a 1 here. So we can just take 1/2 of row 1. Will get us down to there. Again, 1 divided by 2. When we do that, we're going to get 0 in that column. We're then going to get the 3 halves, 1/2, and negative 1/2 there. Okay. So once you have that, okay, you're now into the second column here. You're now going to take this row 3. You need to target this one now. Okay. So you're going to take row 3 minus 1/2 of row 2. Okay. So the 3 halves will come from the 3. Okay. And you apply that to what's left. Okay. So you're going to get this. You're going to get that. You're going to get that. This stays the same. Okay. So now you're in the proper format here. Okay. This is x1, x2, x3. So you can now say that x3 here. Okay. So you've got 2x3 is equal to negative 2, basically. Okay. How you would read that. So you divide by 2 and you get x3 is equal to negative 2 divided by 2, which you do here to get negative 1. Okay. Now that you know that x3 is negative 1, you plug that back in to this equation, and you get from that x2 is equal to 0. You then plug that back into this equation, those two things, and it gives you that x1 is equal to 1. Okay. So that's how that works. And here's just a formal algorithm here, the pseudocode to go through that. Okay. Which is going to, I think these are probably easier to see how to solve them rather than the algorithm. But the algorithm's worthwhile as well. So here's one way to do the forward elimination, and here's a better version of this. Okay, you should look through those. Okay, and you see that these are in cubic N3, which is not great. Okay, but it's simpler than doing it the other way around. Okay, so that's the idea for that. We will not do the LU decomposition. There's nothing wrong with it. It's a fine byproduct of this. Okay, the same way with compute a matrix inverse. If you want to look through those, feel free. I'm just not going to ask you those on the test, okay, or in the homework. Okay, I think that being able to do the Gaussian elimination is enough for that section. Okay, so the next section is on balanced search trees. So in algorithms, no, sorry, that's what you're in now. In data structures, I assume that you talked about trees, and particularly binary trees. Okay, and we've mentioned here that a binary search is dependent on the fact that when you look at a node, you know immediately that all values to the left are smaller than it, and to the right are bigger than that. So you can get in the log n search time, right? Well, that's dependent. Doing that efficiently is dependent on your tree being relatively balanced, okay? Because if you have a tree that is super complicated or super unbalanced, okay? So if you were add to a normal tree algorithm, just 1, 2, 3, 4, 5, 6, you would have 1 as the first node, then to the right of that would be the 2, right of that's a 3, right of that's a 4, and so forth. So the search algorithm there, the binary search, doesn't help you at all, okay? It only works cutting it down in half when you have a balanced tree, okay? So that's the idea here. So we want to keep this efficiency at the log n. Okay, so where it's worst case is n, because we want to make sure our tree gets balanced. So there's a lot of effort has been expended on this in trying to figure out a way to make these trees balance themselves. Okay, so that's the idea. So the first approach here we're going to call self-balancing trees. Okay, it's the idea that when you're adding something to a tree, it will determine if that addition will cause the tree to become unbalanced. And if it does, then you'll do a rotation or some kind of a switch. Okay. The big one there that we talk about, we'll see some examples of that's an Avl tree. Okay. And it requires that the differences for every node between the left tree and the right tree is no more than 1. Okay. So you never go very far off. Okay. There are also red-black trees, which we won't really talk about, that tolerates a height of one subtree being twice as large as the other. Okay. And again, the reason for this difference with the Avl tree, it requires more work to maintain than a red-black tree would. Okay. So you have to figure if the results justify that extra work. Okay. So both of these work with some rotations we'll talk about in a minute here. Okay. The other way that you can do this is that you can decide to allow there to be more than one value stored in your tree node. Okay. When you do this, it defers having to split things up. Okay. Which costs. Okay. So with this, you get down to the idea of the 2-3 trees. Okay. And 2-3-4 trees. So a 2-3 tree allows 2 element trees and 3 element tree, or 2 element trees, which is normal, 2 children or 3 children basically, and then the 2-3-4 allows 4, of course. And then we're going to get to B trees later. B trees are very important. B trees are used a lot, so we're going to talk about those in chapter 7. Okay. So this idea of the Avl tree is the idea that we're going to keep this balance factor. Okay. So the balance factor then is going to be either a 0, a +1, or a -1. Okay. And if it goes beyond this, then we've got a trouble. Okay. And we just calculate that. So for example, in this one, we'd start at the leaf node, the one up from leaf node. So at this node that has a 4, it has 0 + 1. Okay. So it's got a 1. Okay. This one has so then over here, it has so it has only a right child. Okay, so it's got 1 + 0. Sorry, 1. That's not correct. It's the left child is a +1. Okay, the right child's a -1. So we have a -1 here. So we're good. Okay, and then as we move up, this is a -1, +1. So it's a 0. This one is a 1 child to the left. So it's a +1. So this one has a 0 over there, 1 over there, difference of 1. That's balanced. Okay, that's an Avl tree. Okay, in this case, we again have a 1 because we only have a left child. We have a 1, -1 because we only have a right child. Gives us a 0 here. Okay, this one has a 0 over here. Okay, but the height of this one is going to be, there's 1, 2, 3 over here. There's only 1 over here, so there's a difference of 2. Okay, so this is not balanced. Okay, because there are more over here than there are over here. Okay, so that's the idea. Okay, so the way we do this is through rotations. Okay, and the rotations work. There are 4 kinds of rotations. There's a single left, a single right. There's a left right, and a right left. Okay, so here, for example, if we find that we're at a 2 and a 1 and a 0. Okay, so it goes all left. We're going to rotate that, basically grab this 2, make it the new center. We've solved that one. Okay. The other way around, if we have the left rotation, if we have a -2, -1, 0, again, this -2 means that it's not an Avl tree. We would rotate that. If we add a node here and this becomes -2, we would then pull that middle one up. Okay. So with the left right, we have something that's a little different. Okay. It goes from a 2, you have 1 left child here and 1 right child there. Okay. And the idea behind a left-right is that we have to temporarily do a left inversion or a left rotation here, okay, in order to get it all set up to be able to do a right rotation. Okay, so a left, then a right. If it's turned the other way, you do a right, then a left. Okay, those are double rotations. Okay, and because we're checking every time we add, then we're guaranteed that this is the only thing we're going to get. We can't get any other funky kinds of notations. Okay, and then the book is going to go through on those rotations, okay, and show you how we would transform. Okay, so in this case, we're constructing an AVL tree. We're given a list of 5, 6, 8, 3, 2, 4, 7. Okay, we start with our 5. Things are good. We add the 6. The 6 is bigger than the 5. It goes here. We're at -1, 0. We're good. Okay, we then add the 8. Okay, the 8 is bigger than the 6, so we're at a right. Okay, when we have this kind of a situation, we have to do the left rotation, whereby the 6 is going to be pulled up as the new root, and the 5's to the left, the 8's to the right. So now we've restored order here, okay, with the 6, 5, 8. We then add a 3. 3 goes over here. We're only off by 1. 2 here, 1 here, so we're good, okay. And then we add a 2, which now rebalances again. Okay, we got a problem here. The problem starts here. We start at the bottommost part, okay, and we are going to reverse this one around. Okay, so we have these 3 that are the issue. So the 3 comes up to the new root here, and then the root at this level. I mean, we're just doing the subtree. It's the root of the subtree. The 2 and the 5 are there. We're still good. We're back to good. Okay, that was adding the 2. Okay, we now add a 4. 4 gets added here. We're messed up again, and now we're messed up in those confusing ways. We're going in both directions. So this is going to give us a left-right, okay? And on the left-right, we're going to, the 3 and the 2 remain the same. The 4 is going to move up here, okay? And we're going to move the 5 up to root and the 6 over this way. So we're having to do more rebalancing, okay? And then finally, when we add the 7, it goes too far, but we'll do a reshuffling here with a right-left. So it's the opposite problem this one had, which will get us to this, which is a balanced tree. Okay, so I think those are relatively straightforward to work through, hopefully. So you can take your time on those. Okay, so the 2-3 trees, look through it, but again, no homework and no test on that. It's just the idea that you can have more than one node. Okay, so as an example here, you have a 9 and then a 5, 9. You can have up to 3 here. So the 9, 8, sorry, 5, 8, 9, all can be in the same node. You then split it up when you get to 3, okay? And you keep going along. And here, when you add the 3, rather than breaking it, so you have one extra level, you can put the 3 and the 5 together there, okay? And then when you add the 2, then that gets broken up by this coming up to the top and so forth. Okay, so again, there'll be homework examples just of the AVL trees and those rotations and not on the 2-3, although the 2-3 are not much different. Okay, the next section is on heaps and heap sort. Okay, so hopefully you've talked about heaps in data structures. If not, heaps are an interesting data structure. Okay, so we're going to define a heap here formally. It's a binary tree. It's not so the binary tree that has keys that are assigned to its nodes that has the following 2 conditions. Okay, so it doesn't have all the conditions that a binary search tree does. Remember, binary tree just means there are 2 nodes. Okay, and the 2 properties of a heap is kind of like when you do a partition and that it's not quite sorted, but it kind of is. Okay, the heap has these properties. The shape property means that the binary tree is essentially complete. Okay, which means that all the levels are full except the bottom level, where only the rightmost leaves can be missing. Okay, if it doesn't have that shape, it's not a heap. Okay, and then the more important here is the parental dominance or the heap property. Okay, the key in each node is greater than or equal to the keys for all its children. Okay, so what this doesn't So you think, well, isn't that a binary search tree? What it doesn't do, it doesn't guarantee that everything is in the same side of a tree that you would normally think, okay? So for example, we have here in figure 610, there's a heap, okay? We have 10 at the top, we have an 8 to the left, okay? The left and rights, we don't say anything about, we don't care about that. We just say that the 10 is the biggest element in the array, and it is. And we say that the 8 is the biggest, not array, biggest element in its tree. 8 is the biggest in its subtree. 5 is the biggest in its subtree. Okay, and we've got a tie there, and that's okay. Okay, but this in no way is like a binary search tree when you look at this. Okay, because on the other side you have a 7. The 7 and 8 would be switched in a binary search tree, but it's still true that 7 has parental dominance over the 1 and the 6. Okay, that's how that works. Okay. And this tree is essentially full because the only 2 missing, or there are 4 missing, sorry, 5 missing, are all at the right side of this bottom level, okay? We usually do this in an array representation, okay, where the 0 will have nothing. Sometimes it'll have what the largest value is. It starts at the root, okay, and goes down, so that the first so many of these are going to be the parents, and then we have the leaves after that, okay? So there's lots of other things we can talk about here. We normally put the H0 is either unused, or you can put some sentinel value there who's greater than everything in the whole list, and you can put 11 there or something, whatever. We won't use that much, okay? So this is how we get to this whole idea of the heaps, okay? So with the heap, there are 2 ways to construct them. When you have an existing structure, okay, from a list of keys, we can do it from the bottom up, okay, in which we're going to create a tree, binary tree, any which way we can, okay? So just in whatever order. So in this case, we have the list 2, we're going to put a 9 and a 7, we're going to put a 6 and a 5 and an 8. We don't care about anything, okay? We're then going to go through and start checking those parental dominance things. So we start on the right here, we look at the 8 and the 7. Well, the 8's bigger, we got to switch them. Okay. We look over here, we look at the 9 and the 6, that's okay. We look at the 9 and the 5, that's okay. Okay. Now we look at the 9 and the 2. Okay. 9 and the 2 is not okay. So the 9 goes up there, 2 comes back up here, which triggers us having to check the 9 against these 2. Okay. So 2 is not bigger than 6, and 2 is not bigger than 5. So 6 moves up there. Okay. And that's how the bottom up construction works. Okay, you throw it together any way you can, then you check to see where it's wrong, and you swap. Okay, the other way, of course, is the top down. Okay, so with the top down, okay, the idea is you're going to add it as you go. Okay, so let's see. They don't have a picture of that. Doesn't look like it's less efficient, so we don't tend to do that. Yeah, so they're not really going through that one much. Okay, so where this becomes interesting is this idea of a key deletion. Okay, so the key deletion here is that it's going to be able to remove the highest element of that. Okay, so when we're deleting the root's key from a heap, as it says here, the key to be deleted is dropped with the last key, after which you then heapify that one. Okay, so we have this 9, 8, 6, 2, 5, 1. We're going to swap the 9 and the 1. Okay, we then get rid of the 9. The 9's removed. Okay, and then we go through and reheapify everything. Okay, to see where we end up at. Okay, so that's the idea. So because of this, because at the end of the heap, if we have a max heap, which we wouldn't talk about here, the biggest element is on top. You can also have a min heap, which has, I guess you would say, parental submission instead of dominance, which means the opposite, that the smallest element is at the top of every group. Okay, but with this, the idea behind a sort is that you just turn things into a heap and then swap out the last one to the end. Okay, so in this case, we have the following. the 2, 9, 7, 6, 5, 8, okay, we're going to go through a heap process there, okay? And when you heapify it, you get this 9, 6, 8, 2, 5, 7. Again, it's not, so the 9 goes to a 6 to the left, an 8 to the right, the 8 goes to a 2 and a 5, and the 6 goes to a 7. The 6 can't go to a 7. No, the 8 goes to a 7. The 6 goes to 2 and the 5. Okay, so this is okay. This is a heap, even though it's not sorted. Okay. Then the idea with heap sort is we take this 9, which we know to be the biggest, we move it to the end, we put the line there to say, yes, now that's sorted. We now heapify what's left. Okay. When you heapify what's left, the next biggest item comes to the top, you take it off. Okay, and then so forth. You go from there. Okay. So that's what you get. Okay. So this means that we have an n for, no, sorry about that. We have an n log n for the first stage for the heapify. Okay. And then for the second one, I guess, nope, that's incorrect. We have an n for the first part, n log n for the second part. So we get an n log n. Okay. So that's the time efficiency. It's n log n for the whole thing in both the worst and the average cases. Okay. So this is the same thing as the merge sort. Okay. And it's a fine sort, nothing wrong with it. We tend not to use it. Okay. Because for one thing, I think it's harder to get your head around than is the merge sort. Okay. And also it is shown, the timing experiments show that it can, it runs more slowly typically than quicksort, but it can be competitive with merge sort. So, it's not a bad algorithm, but we tend not to use it because merge sort just seems to make more sense to folks. But this is another sort you should understand. Okay. And there'll be some homework from that. Okay. 6.5 on Horner's rule and binary exponentiation. It's a fine section, but we're not going to cover it. Okay. If you're interested, read it. That's fine, but no homework, not in the test. Okay. It's more mathy than we went to get. Okay. It's already a long video. We're not even any further. Okay. So skip all of that section. Okay. Then problem reduction. Again, I think we're just going to talk about and probably not do a lot with. This is the idea that you're going to convert a problem into a different problem where you know the answer to. Okay. And this first example probably will serve as what we're talking about well enough. Okay. So we've already done the GCM. There are lots of good algorithms for GCMs. Okay. Greatest common multiple. Okay. So we'll take a look at how we may work on that. So the least common multiple, then we define that of between two positive integers m and n is going to be the smallest integer that's divisible by both. Okay, so the LCM of 24 and 60 is 120. The LCM of 11 and 5 is 55, and so forth. Okay, we talk about this a lot. Okay, and you probably remember you may teach doing this, following the middle school method there. Okay, which is involved with prime factorization and all the other stuff, kind of like we do with the GCD. Okay, so with this one, we haven't found a great way to do this. Okay, so yeah, but we can convert it via this formula here to a GCD for which we already have a good algorithm. Okay, so if we're trying to find the LCM of m and n, we can redefine this as m times n divided by the GCD of m and n. Okay, so we know m, we know n. We have good algorithms for getting the GCD of m and n. We can then calculate the LCM this way. We transform it into a different problem to solve it. Okay, and then give other examples here on counting paths in a graph where we're doing these different. So the idea behind here, I said I want to talk about, but I will because it's interesting. If we have our adjacency matrix for graph A, then A squared, okay, becomes the number of paths of length 2. Okay, and we can that's what this notation means. Okay, so this is the way we can count the paths in a graph using that. Okay. And the rest of this, I don't think, we may talk more about linear programming later in another chapter. I don't know if we're going to get that far or not. Okay. But that just gives us kind of a quick little overview of that. Okay. And here's the, I think we already, did we already do the, yeah, we talked about the wolf, goat, and cabbage puzzle. This is the way to reduce our problem to a graph problem and find the solutions. Okay. Yeah, I don't think I'm going to give any homework from this section either, but it's interesting stuff. Okay. So that's it for chapter 6. I'll probably put out the homework tomorrow, would be my guess. I assume you're still working on the last chapter's homework at this point. Okay. So again, just to review, this is the last bit of material we're covering for the midterm. So it means next week, next Sunday, there'll be a video out that's a review video. And the Thursday that week, Thursday meeting that week will be a review over whatever questions you have about anything. Okay, there won't be a homework assignment for it. Okay, and then starting on Friday, I'll open up the exam from Friday to Sunday in order for you to be able to take that. Okay, and again, if you need different times, let me know and we'll try to work something out. Okay. Okay, that's all I've got for this week. So I will see you guys on Thursday for our normal session that I will hopefully record.